It's down to the groundwater and goes from the groundwater to the river. We call that RGW for the groundwater flow. These are two different runoff components. The infiltration, now I come to your question, is this process. Is it going into the soil, infiltrating to the soil, changing the soil moisture storage? Then maybe it goes back to the plant and evaporate again, could be. Or it's producing runoff at one of these three pathways. Yeah. So the infiltration is a process within the system. It's not directly, you cannot say infiltration is part of R or part of E. Is it clearer a bit? Yeah. So these are the three runoff components. Of course, then you can have back from the groundwater, so capillary rise back to the soil water, that can happen, or back again to the groundwater and all sorts of things. Or into the vegetation, so root water uptake in the vegetation. It can evaporate. We call that usually ET for transpiration. Yeah? These are different evaporation fluxes. Is that clear? What the infiltration is, and all these parameters together I make blue the runoff components, surface runoff, soil water runoff, groundwater runoff. These are these runoff components. We have different evaporation fluxes, for instance, interception evaporation, transpiration. We can have ES, soil evaporation. We can have also evaporation out of the water directly. I also call that ES for a moment. You could also EW, or what depends on how important that parameter is. These are different evaporation fluxes. And we have different DSDTs. These are different storage changes per time steps. For instance, a change in the deception storage, change in the soil water, change in the groundwater, change in the channel itself. Yeah. And these are different DSDTs. Huh? And the DSDT make hydrology interesting. And Cinderella, of course, but also the DSDT. Clear again? Some of you couldn't be there in the first afternoon because of other appointments, and I explained this quite into detail. I'm not sure, is my lecture already online? I don't know even. Mr. Cameraman, is it already online? Not yet? Or yeah, maybe in the break you come down and write it down. If people want to watch that part of the lecture again, it's already available. And he gives you a link, or the folder where you can find it. Clear? Now the magic comes, does this blackboard disappear again? Because last time we had this problem getting it down again, and we succeed. Okay, we explained stage discharge relationship, and this is a hydrograph we said. Huh? That's the discharge change per time step. That's this outflow out of a catchment, yeah, at the end, at the gauging station. Let's look at a hydrograph over a longer season. This is from May till August, a few months in catchment in Virginia, I think. You see here different, it's going up and down. There was a big rainfall event. This is this black bar here. Yeah, this is precipitation up to 70-something millimeters per day. This is per day, you know. Wrong unit in the textbook, unbelievable. I took it from a textbook, and it should say millimeters per day, not just millimeters. Huh? We are very careful with our units, aren't we? So I should correct this, but I copied it from the book of Hornberger. So these, you said 70 millimeters per day rainfall, and that causes then a big discharge event. Discharge goes up from 0.2 or something to 1.5 or so. Yeah. Going up and down again. In the summer, in July, you have then a low flow period where you have no rainfall or just very little. And then you don't have much discharge because it's just basically a recession curve. Yeah. This is a low flow part then, and these are high flow peaks. Yeah. That's how a discharge curve looks like. Of course, in different climatic zones, it looks differently. The challenge is to have a discharge station that measure these peaks very well, but also measure the low flows well, yeah, to get the full variability of flow. That's the challenge. Let's look at some examples. This is a small so-called V-notch. Here you have a defined surface area, slow flow through area. You have a change here, really a free fall of water from this almost like a little reservoir here behind that station here, V-notch. There you have absolutely quite no turbulence, laminar flow conditions. And then you have a free fall, and this water level here at this point you can directly relate to a discharge value. Yeah? So you measure the water table in this building here, the water table, and this water table can be translated into discharge through some formula and through some calibration measurements. Some other examples. These are so-called flumes. These are examples from the West Bank in Palestine. Here it's just a too wide river. You cannot just put that into one little V-notch. And doing floods, it can rain very heavily in this area. This is near what is it called? Najat. It's north of Jerusalem in the West Banks. And if there's flooding, we even had it once that the flow was not only overtopping this structure here, it was also flowing around and basically destroying part of our nice structure here. What you measure here is the discharge. This is the view from below. It's a partial flume where you have a significant change from these subcritical flow conditions before into supercritical just at the overflow. And that defines a fixed water level when for a given discharge through this structure. You can calculate that with this formula, and the width goes in, and then the water level, the width doesn't change because it's all concrete. The water level height changes. That's what you measure continuously with a pressure transducer, and then you have a coefficient that depends a little bit on the structure, which you can calibrate through some calibration measurements. But that's basically how it looks like. Yeah. With this, you continuously measure the water level, and then you relate the water level into discharge. Who visited a discharge station before in his or her life? Nobody. I can't believe it. Some. Yeah. You're a mid-career professional, so it must be that you have seen a gauging station. This is one in the desert, and this is in Jordan. And you wonder why do people measure discharge in the desert? But we said that in desert environments, you have a short time where you have very high rainfall, and then you produce for a short period of time a discharge. And here, this is a dryland river, where people were measuring the water level here at this station, and also here with the so-called diver. It's just a small pressure transducer where you can measure this. And then the water table elevation and change you can then use to make a hydraulic computation of the discharge over time at this station. Let's look at some more pictures and it gets a bit clearer. This is the well. You've seen in this picture here, this structure here, where you measure the water table here. And the water table can easily be here 1 or 2 meters high up, doing a few minutes or hours. This is a diver instrument, or that's the instrument, that's the well, but you can lower the diver into this structure and measure the water table fluctuations in this station. Here's the diver in the field. Of course, it's bone dry usually when you do that. To be there during a flood event is very rare. And usually you miss them because there's only flooding maybe for 1 or 2 days, and then none again for the rest of the year. So you must be very lucky to measure this. And then further upstream, that's the other station here. You see this well with some holes in there that water can also enter and that you can measure the discharge. Well, during floods, there's a lot of sediment transport also in these rivers. All these gravel here on the surface is then moving around, so it's also very dangerous to be in the bed here during floods. It's more people drown in arid environments often than they die because of water scarcity. And Bedouins usually no. Sometimes you have some tourists that do camping in these riverbeds. Of course, that's crazy, because a flood peak can just come in within minutes. And then you and your tent all washed away. You're part of the sediment transport then. But the sediment transport can be very efficient. Therefore, you also have to really do that with a real steel structure. And sometimes trees or pieces of wood and so are transported, and then even these things can collapse. These are other gauging stations. This is the old bridge in the Abai, in the Blue Nile in Ethiopia, where people measuring since many decades. It's the Blue Nile there has a very narrow canyon type of shape with hard rocks on the side, you see here. Because to put a lot of concrete there and try to kind of divert the Nile somewhere is a bit difficult. Can be a huge river. Huh? This is the Blue Nile. It's actually brown. Huh? It's not so blue anymore. A lot of erosion in there. But Abai, I've been told by the Ethiopian colleagues, means brown, isn't it? Abai? No? It's not true? I'm not speaking Amharic. Did somebody tell me some nonsense here? Okay. Here's the old bridge built by the Italians in the 30s, I think. And here below there's a measurement station here where they measure the changes of the water table here. And then knowing the cross-section and some velocity measurements that help them to transfer the water table changes here into discharge changes. This was just at the time where they built the new bridge. You see it here in the back. Maybe some of the Ethiopians passed that station recently. And now you have a nice, almost motorway going over the Nile. But it's much faster nowadays to cross the Nile. But I took this picture in 2005, 6, something or so. And then it was still the old bridge. Running for Africa, but they're all based on poor data sets. Yeah? And therefore, contributing to your research to help with measuring the discharge is a very useful investment of her time and of her money. And so what she and colleagues did, they built this structure, and this is a low flow situation. You see here, so much water can be discharging there. That's how it looks like. Usually when I visit her, I said, well, great, fantastic. Good that you measure, because only then you can calibrate your model in a much more meaningful way than only just another model based on poor data sets. Here is the diver in this thing here. You see this concrete pin, and there she has on a cable an instrument which is down here measuring the water table fluctuations in here. Oh, very nice. She was there. We looked at it. Beautiful. Then she came there the 1st of March in 2006, and No, she came there on the 28th of February 2006, and it looked like this. There was no discharge whatsoever. All water upstream was abstracted by farmers. They all used it for irrigating their plots. Yeah? So no discharge. And we said, well, yeah, okay, that station is probably okay. Then on the 1st of March, we had a major rainfall event, and she came then one day later, and the same structure looks like this now. You see here, big boulders were transported. Huh? You know, this is not a thing you can just pull. You know? The whole thing is destroyed. Here, all the concrete is kind of partly gone. Here, this was where this concrete pin was standing there with her diver, with her instrument to measure the water discharge, all gone. You see here some sediment from this big flood, so the water table was all the way up here. You see here some deposits of some wood. Yeah, so the water table was all the way up here. So it was completely too high. The structure was underestimated. So we, or she, together with some Tanzanian colleagues who designed it, underestimated the discharge we can have in this field. And it was really flowing, and the whole thing basically was destroyed. Too bad. This was her measurements. The water table, now it's time. It's a bit difficult to read. I apologize for that. This is 2 afternoon, 2 lunch, noon. Yeah? This is 12 o'clock noon. This is 2 in the afternoon, 4:45 in the afternoon, 7 in the evening, and so on. So these are roughly 2 hours. You see, no discharge whatsoever in the morning. Yeah. Then there was really a bang, yeah, a very intensive rainfall event. You have a little bit of pre-peak, and then the water table from 0 up to 40 centimeters, going down again to 10, 20 centimeters, then up to 2 meters, so a waterfront of 2 meters. This rise is only a few minutes. Yeah, a 2-meter waterfront came in, and then no measurements anymore, because then the diver was washed away and couldn't measure anymore. But she found the diver, so that was very good, because these measurements she read out from the data logger in the diver. Otherwise, we wouldn't have any data. But fortunately, she found it a few hundred meters downstream. The river deposited it somewhere. But you see, we don't know what the really highest peak were. But then we had a smart farmers. Farmers are usually very smart. He went there and read the water level and wrote it down every 2 hours. Yeah, and these are handwritten water level measurements from him. Every 2 hours he was reading you. But you can see within half an hour it went up to 2 meters. We don't know exactly what the highest peak were, because the thing was then destroyed. Maybe it was up here or maybe only here. We don't know. And then it went down again. But also within 1 hour, the discharge is going down again. You see how dynamic that is, huh? This is not a desert. This is a semi-arid catchment. Yeah. That was another gauging station here. I'm standing, smiling, proud of her. This is Maluz, by the way, with some this is a master student. He was sitting in the class in 2005. He did his master research on this. And a Tanzanian, Zimbabwean PhD student and a Dutch master student working together. I'm smiling. I was very happy. They are measuring. That's good, I thought. Yeah. This was the structure. No discharge at the time. And again, on the 2nd of March, she came along, and that's how the structure looked like. And we all learned our lessons. Yeah. This is taken from the internet from another event in the H.J. Andrews. I showed this phenomenal rain gauge, this kind of huge wooden thing, which I showed in my last lectures. Do you remember? The Russian-style rain gauge, they call it the biggest I've ever seen. That's the same catchment. This is a small side valley, about 1 kilometer square. Watershed 1, they call it. And usually this river comes from the side, goes under that. This is a forest road, and then there's this is a bridge. Goes under the bridge and goes into this river. And it's 1 kilometer square. It's a small river thing. Huh? And then they had a huge flood event in '96, and there was huge tree and sediment transport. The thing was basically blocked, and the water was just flowing all over the place. Huh? There was a gauging station. The gauging station is gone, and you can imagine that during floods, how difficult it is also to really measure discharge. Yeah, so you have to get these small low flows of a few liters per second, but then during this times, water is flowing just everywhere. How can you really channelize all that water and do a proper discharge measurement? Very, very difficult. Huh? You see, therefore, all flood peaks are usually wrong. Yeah, usually we reconstruct them with some hydraulic computation, some formula where we try to estimate the flood peak, but it usually has quite an error because nobody was then there. Here, fortunately, some people were working there and saw it and could measure it, but usually it's happening on Sunday evening or so. Nobody is there. Nobody really has measurements. It's also too dangerous often to go there, during flood times, certainly in the deserts. So all flood peaks, even if they come from a nice database from the official geological survey of your country, they're usually wrong. Yeah? So please don't forget that, because this is how a flood looks like. Yeah? I show you a video. I promised a video from the Appalachian Mountains. Actually, I show it I bring it during the break. But maybe I have that. I check if I have it still here from last year. No. No, I will bring it during the coffee break. Sorry, I show my movie later. Good. Now let's go to interpreting discharge. This is a discharge, how it looks like at the Meuse. The Meuse is one of the two main rivers flowing into the Netherlands. The Meuse is coming from France, Belgium, a bit of Germany into the Netherlands. There they have very long discharge records, more than 130 years or so. This is the discharge since 1911, 1900, yeah, up to almost 2000, so 100 years of data. Very nice. Usually we don't have so long data sets. There's also a challenge nowadays. We always talk about climate change, but usually our discharge data, we are lucky if we have 20 years of discharge, certainly in developing countries. But the last 20 years, how representative are they for a longer time? We have very few stations where we have more than 100 years, very few around the world only. You see, this is the long record. You don't see any trend, I suppose. And here, somebody zoomed in, and you see the variability on a daily basis. You have a big peak in spring, February, March, something, and then summer low flow, winter higher discharging, and you see a lot of variability on a daily basis. Generally, we can classify rivers according to the following scheme. We have ephemeral streams. These are streams that are flowing maybe once a year or twice a year. And this is a monthly discharge, but maybe they're only flowing for a few hours. Yeah, looks like they are flowing here a full month. That can be, but ephemeral could also mean that they only flow for a few hours. The picture I showed you with the desert situation in Jordan, that was a river. You don't have a discharge event every year. Yeah, maybe every second year, maybe then 5 in 1 year, but then another year with nothing again. So very huge variability. That's what we call an ephemeral system. We have intermittent or seasonal systems where you have very pronounced seasons. For instance, a wet winter season here, November, December, January, February, and dry summer, low flow, where even the river can completely disappear, discharging. This is the situation we have in this Tanzanian catchment. In the dry season, no flow whatsoever. In the wet season, a couple of events maybe flow for a couple of weeks, but then it disappears again, and so on. Or we have a perennial system, which is continuously discharging, so there's always above zero. It's never zero, but there's a lot of variability depending on seasonal variations. This is usually what we have in a humid temperate zone here in the Netherlands, Germany, etc. So know these words, please. Now we look at another way of classifying them. The first one is from Tennessee. It's a pluvial system. Pluvial means dominated by rainfall. What you see here is a hydrological year, 1st of October till 30th of September. That's the way the North American colleagues break the year in this region. You have a couple of winter events, which could be some snow as well, but mainly it's rainfall in that region. And in the summer, you have almost zero. Maybe it is even zero here. I can't see it. And then some events depending on some heavy summer rainfall. And you can have very heavy summer rainfall also in Tennessee. An episodic regime is like the ephemeral system, which I just showed before. Dominated regime from Montana. Montana is in the is dominated by Rocky Mountains, so high mountains, snow and ice regime of the discharge, and so you see almost no change in discharge, very low flows in the winter from October or starting already in September till kind of March. Why is that? Just too cold. Yeah, all the precipitation coming in is falling as snowfall. Yeah, and the snowfall sits there and waits to get melted, and that only when it gets melted becomes hydrologically interesting. So you see in March some first events, and then mainly in May, June, July, you have most of the snow melt peak coming in. It could be that this is also supported by some rainfall events, but most of the volume is generated through melting snow and some ice as well, maybe. That's what we call a snow melt regime or nival regime. Yeah. Fluvial, rainfall dominated, snow dominated, and episodic, depending on in arid climates. Let's look at this for a moment. I want to explain it on a map again. We have here 3 rivers. This is the overall discharge, the Potomac, yeah, with a gauging station down here, maybe with a river system like this. Yeah, this is maybe the overall river, the Potomac. Then we have, I can't read it, the print is so poor, it's the Shenandoah, sorry, it's difficult to read for me from here. That's a subcatchment. Maybe it's just, maybe it's just this system. And you measure the discharge at this station, yeah? And then you have the south. Yeah, this is a very small river, maybe just this one, yeah? Which has a small creek somewhere, side catchment. Yeah, so 3 catchments nested in each other. Clear? Now we look at the discharge response. Can you see it? Overall, we had a huge flood in the Potomac. Discharge went up from 800 or so up to 4,500 cubic meters per second. Yeah. Now you say, well, this middle catchment, I call it middle catchment because I can read it for this. Sorry, reacted first. Yeah, even before the big one, but it went from very little up to 2,000 cubic meters per second. And the south, the small system, you hardly see because it's just a very small river. So you would, if you look at this, you see that the south actually has this peak earliest, and then there's the middle catchment, and then the Potomac. But you would think the most important is the Potomac. But if you want to understand the flood generation for this specific flood discharge, it's more useful to not look at the cubic meters per second, because this is just a small river basin, the south. It's better to look at the discharge divided by area, so-called specific discharge. Now you have cubic meters per second per kilometer square. Yeah? And if you now plot this, you see that the south actually is the one which is responding first and the most dramatic. So the specific discharge goes from little to 0.4 cubic meters per second per kilometer square. The middle catchment only to 0.3 roughly. And the Potomac reacts later and has a lower specific discharge because it's a much bigger catchment also and maybe did not get overall so much rainfall as much as this little south get. So if you want to compare different catchment of different size, it is important that you divide by area. If you just look at cubic meters per second, it's very misleading because bigger catchments always have more discharge. Yeah? But you have to divide by area to really be able to compare them. The same would be if you would put here millimeters per day or millimeters per time. Yeah? Because millimeter is liter per meter square. You remember the discussion why we give the water balance parameters in millimeters? Yeah? Liters per meter square is 1 millimeter. So it's per meter square or per area. and that divides the area, puts the area in the denominator, and then we can compare different rivers quite nicely. Also, if you compare different neighboring catchments, if you don't divide by area, you might really be misled concerning the processes. Now the rainfall, the discharge response of a catchment. You see here the rainfall record from October till October, or end of September. This is a catchment where there's almost every month, there is every month rain. Maybe a little bit more rain in the winter half year than in the summer. But even in the summer, you can have almost every day rain. And it also rains at least a few days per month. Then the discharge response looks like this. You have the highest discharge in the winter time, yeah, from January till May or something, or June. Yeah. But a very irregular response. That we have the highest discharge in the winter, but not necessarily it's difficult to say on this figure, but not necessarily much higher rainfall in this time of the year. What can be the reason for that? Some DSTT, that some water is stored in the soil zone or snow and ice and only discharged later. That could be that some of this rainfall, not all discharges in January, February, but only comes then with some melt events during this time of the year. Or the different evaporation. Of course, in the summer, usually we have much higher evaporation than during the winter times. What you also see here is two different response patterns. You see here, if the discharge is very dynamic, you see here very spiky response. Really, every bigger rainfall events directly are visible in the flood hydrograph. You see direct responses, but then also low flow or dry weather flow periods where the discharge is going down again. Certainly, you see that here in the summer when all these small rainfall events. Again, a wrong unit. Huh? What is wrong on this unit? Millimeter per day. You know, it says daily rainfall and writes millimeter. Huh? These textbooks, you cannot really rely on them anymore. Huh? So it should be millimeters per day, of course. But you see here, these small rainfall events of less than 20 millimeters, they don't do much to the hydrograph. Huh? It's basically from June onwards a falling limb and a recession dry weather flow. In this part of the year. So what is happening to this rainfall during the summer season in that catchment? Most is stored in the soil, I suppose. Yeah, maybe it could be some reservoirs as well, but we don't know. But basically, it's the unsaturated zone. Some maybe on the vegetation, some also maybe in the groundwater. But that the discharge is always going down. What is happening to this water? Most of it seems to be evaporating. Yeah, that's what you see here in this summer period. Yeah. You can also explain these dynamics with a two systems approach. That you have one very fast responding spiking directly depending on the rainfall events, and one much more damp seasonal behavior. That's this black line. It receives a lot of recharge during this time of the year. Reaches its maximum when it comes to discharge, so the low flows don't fall below that black line, which is a constructed line, I need to say, don't fall beneath here, and that's kind of a long-term discharge contribution. Yeah, where could this water come from? Remember again what we discussed about the different runoff components. I hope you can still read our drawing here, the different R's. We have overland flow along that hill slope directly. We can have some sort of interflow in the unsaturated zone, partly saturated zone, or some groundwater flow during the river. Yeah. If you now look at these two systems, how would you, which component are responsible for which system? This black line, what kind of discharge should that be? Is that the overland flow? It's probably the delayed groundwater flow, which has much more seasonal behavior than a kind of short-term dynamics behavior. And then these fast, spiky one is like the overland flow or some sort of fast runoff generation. Could also be subsurface storm flow. Looking at different dynamics of rivers again, this is an example from a river in Pacific Northwest of United States. They did a lot of work in looking at the variability of flow. it's very important from an ecological point of view that a hydrograph has its original variability, because it's very important for the habitats, for the ecosystem. Therefore, they were classifying low flow situations, the green and the red one, low flow or extreme low flows below a certain threshold, but also all sorts of different high flows, seasonal high flow, extreme high flows, which is kind of large floods, which is this system here. And it's very important that this variability remains. If you build a dam, of course, you reduce a lot of that variability, and that has impacts for the sediment transport and also for the ecosystem conditions downstream. Different ways of parameterizing that. And here again, low flow. I don't want to go too much into detail. We do, if you're interested in the linkages between flow variability and ecosystems, ecosystem requirements, I recommend to you to follow the course on environmental flow requirements, or environmental flow. It's a short course, optional short course, where we go more into detail into these things. Going back to these two systems, what we saw on that one hydrograph was a delayed, probably groundwater system, which has more a seasonal, very damp behavior, and then the very spiky one, which is more, can be attributed to surface runoff. You see here that rainfall can be flowing through a fast runoff and a slow runoff, and then creating this runoff response. Having these two different flow components, they have complete different dynamics, yeah, but they also have different chemistry. That's also very important, and you can see this on this figure. Here you have a very dynamic system. The discharge from 0 goes up to 20, 30 liters per second. It's a small river system. And what you see here is a chloride concentration. During the low flow situation, chloride is at 25 something millimole per liter. Then it goes down to 15, and then up to 20, 25 micromole per liter. Yeah. How can you explain this change of chloride during this event? We only break for coffee after you explain me. So. Yes, please. Yeah, it could be that the chloride comes from agriculture or some non-point source pollution. Yeah, yeah. But even if it would be a natural background chloride, what could be that we have such a change of the chloride during the event? Why is it going lower during the early parts or during the peak of the event and then going up again? Any idea? Sorry? Yeah, leaching. How can you explain me a bit better what? Yeah, could be that during the overland flow, salt is washed into the system, but then we would expect that the chloride increases during the event, and we rather see decrease of chloride during the event. So I don't think that this is the dominant process here, but it could happen. What is happening here is that you have overland flow. The groundwater chloride concentration is during the low flow situation here, and then heavy rain comes in, and you have water contributing to discharge, so to runoff formation with lower chloride, because the rainfall has lower chloride in this area. Therefore, this surface runoff causes a decrease of chloride and then increase again. So a change of chloride, we do the same. We explain that in detail in the tracer hydrology environmental isotope course. We do the same with the environmental isotope composition of the water and with other tracers, and then we can separate the groundwater or old water discharge from overland flow. Yeah? So chemistry and isotopes help us to understand how much water comes from groundwater and how what overland flow contributes to stream flow. Yeah? Yeah. My voice needs a break. Can we have the 15 minutes break now? We are slightly over time, and I explain it again directly after coffee break. Yeah, thank you.